And here are several notation in reinforcement literatures. I will use
okay, so let's outline that something. This is important. Right? Something. First of all, are you able to get the previous page, next page?
Yeah, I will talk about problem set.
Can you go to the previous page? All right. So are you the value-based reinforcement? Are you going to talk about us or now? This is just a second policy-based.
I will talk about the random.
What?
Random. I will introduce Q-routing first and talk about our policy-based.
So the value-based is for somebody else in the existing literature, right?
Yeah.
And then you go now talk about policy-based.
Yeah.
Right. So this is your joint work with the Professor Chen Yi.
Yeah.
And I'm curious that she's never been here. She's not interested in reinforcement anymore, right? She's still interested.
She's interested, but her research field is not reinforcement.
I see. Okay. Right. All right. So now I got the question. Okay. Why do you need to put something? There's one button, right? You click it, let's go to the next page, right? Why you need to do a system? Does he need help? Are you in the display mode? Is this in the presentation mode or something? This button is the next page, right? Just click one click, then you go to the next page. Click on the next page. Why do you need to click? View, presentation or something. View. Go to slideshow, enter the full screen. Slideshow, yeah. Okay, we need to click one click. That's it.
Oh, okay. Okay, try. Hold on. Try again. No, doesn't. Okay. Yeah.
We go to slideshow and to full screen.
I mean, it wasn't in the full screen.
Maybe in the full screen.
There's basic definition in reinforcement literature.
You should stand up. Right? You should go to the slides. Or you talk to the computer. Is anybody online?
No.
They are online, right? Some people. Yinglu is online. So maybe that's okay. Because online you talk to there, that's maybe okay. But it's awkward. This is awkward. You should write presentation, you should talk to the facing audience, right?
There are basic definition in reinforcement literatures, and we can quickly go through these definitions. The first one is a long-term cumulative discounted reward, and the second one is a presumption-Bellman equation. Okay, let's enter the problem setting for network routing. And there is a figure about one particular communication network structures, the 6x6 grid topologies. And the problem is here, for example, in these pictures, each node can be understood as a source or destination. And for example, if we have a waiting buffer in this node, some packets wait here, and then if a packet, the destination of a packet is other node, for example here, then we need to choose the next node, a variable link to send the packet. For example, for this node, only two variable link here, this one or this one. And the routing is the decision making about directing data packets from their source node towards their destination node through some intermediate nodes. For example, if the source is here and destination here, and all of the nodes between them can be understood as intermediate node. And each packet should be hopped one by one. And our objective is to efficiently utilize the communication paths and minimize the average packet delivery time, not minimize the number of hops as the average time. And the delivery time comes from the transmission delay and the queuing delay. The transmission delay is the time a packet spent on the link. In our experiment, we set the transmission delay on each link. We use a common constant. All the transmission delay is the same on one link. And the queuing delay depends on the time the packet spent in the waiting buffer. Here we consider an infinite buffer. So let's talk about how to apply reinforcement learning to network routing. Here are some perspectives about how can we consider the problem as a reinforcement learning problem. The first one is we can use single agent reinforcement learning to optimize each router. For example, we can consider each router as an independent agent and optimize it independently. Maybe use some local information, then each router in some sense will behave selfishly, since they will try to maximize their own profit to minimize their own packet delivery time. And our objective is to use a multi-agent reinforcement method to solve this problem. Consider the network system as a whole agent and update each router through distribute optimization. Then the multi-agent cooperation and coordination will be considered by each router, and the routers will consider cooperation to reduce the whole average delivery time of all packets in the systems for long-term perspective. So we consider the problem as a multi-agent partially observable macro decision process. Since no router can observe the whole state of the system, so it's partially observable. And I will talk about the queue routing, the earliest and most famous paper. The idea is interesting but simple. For each router, or we can say a reinforcement agent, the state is the destination of the first packet waiting in the router's waiting buffer. We only consider the first packet. And the action is one of the router's outgoing links. For example, if the node connects two adjacent nodes, then there are only two available actions. And the definition of the reward is a negative sum of the transmission delay between two routers. For example, at time t, if an agent choose send a packet through an outgoing link to one of its adjacent nodes, then we'll know the transmission delay, and the queuing delay for this packet waiting in the waiting buffer of the agent will be recorded. Then after we send the packet, we get the transmission delay and queuing delay.
Okay, so this is something that much easier to share or something.
Yeah.
They can do that.
Yeah, I will use that.
You're going to use a picture to describe it, right?
Yeah.
Okay, next slide. So the still equation. So okay, so go back. Coming back. So what's the reward of getting the something now?
Pardon?
What is the reward? Are you going to use maybe the picture
Here is
using go back, coming back?
here is the reward.
Okay. So I is the agent I.
Yeah.
Reward at country.
Yeah.
What's that again? Explain that.
And if we have the reward, we can update our Q function.
Right. So the question is, what is the reward?
The reward is the negative sum of the transmission delay and the Q delay.
So what is the transmission delay?
I have talked.
So because at the for agent I, it has a agent I is a link called.
Agent I is a node, a rotor.
Okay, so coming back to the previous. Yeah, here. So let's use okay. Yeah. Is a agent I dot?
Yeah, a dot.
Is a line.
A dot.
A dot.
A dot is a rotor, and each rotor is considered as
It has several possible lines, right?
Yeah.
So, like for example, choose this is the I. This is dot agent I.
Yeah.
It can use this link.
Yeah.
Or use this link. Right? It's
Yeah,
a choice, right?
Yeah, choice.
So this link, this agent I has the first packet.
Yeah.
So where's the first packet linked? Is there something buffer waiting for that? For
Sure.
this node?
Sure.
Is that right?
Yeah.
Okay. So this first packet destination is this here, right?
Yeah.
Right?
Yeah.
Destination is that. Right? So the transmission link is the immediate link. Something the transmission delay is using this link is one transmission delay.
Fine.
Using this link is another transmission delay. Right? Okay, transmission. There's also queuing delay.
Yeah, queuing delay depends on the time the packet waiting in the waiting buffer.
Which buffer? This buffer
This
or
buffer,
this buffer?
this buffer.
Okay, so how long has been waiting for this link, this node?
It's when the packet enters this node waiting buffer, there may be some packets in front of that, and it depends on.
So this packet, remember how long has been waiting on?
Yeah, this node will record the packet staying in its waiting buffer.
For each packet.
Yeah.
So now after some time, this packet becomes the front.
Yeah.
The leading. So this packet at this point, this point. So this waiting time, the waiting time or the delay, queuing delay, depending on the packet.
Sure.
Right? Some packet has been long, some packet have been short.
Sure.
Right?
Right.
Okay. So the agent is the delay, queuing delay, depending on packet, not just depending on agent or the averaging or what's something. So that's why I'm asking that definition now. Let's go back to now. Here. Right. What is VIT?
VIT is
the
the
transmission
transmission delay.
Transmission delay on which link?
Transmission delay on the link the agent choose.
Okay, go back to the previous one. So here is right for this link choice, that's one transmission delay. For this is another transmission delay. Now you say this is agent transmission delay. Yeah. Yeah, what?
If the agent choose this link to send the packet.
How do I know which one to choose? Is it agent decision already made or to be made?
The decision will be made by this agent.
Okay, before making, I don't know my transmission delay. Am I right? Or I know transmission delay?
Yeah.
Okay, that's a question, not yes or no. The answer is the transmission delay is so at this point, the decision has been made or before being made. What are we talking about?
If this agent send a packet through this transmission delay, and after the packet arrives at this node. The next node, feedback signal will be sent back to the
So
previous.
this is the historical data. Or what? It's something before. Are we making decision? To make a decision, or the already decision has past decision delay. So let's look at this one. What is this BIT? The history.
Once you do the decision making, you know the transmission delay.
Once the decision, okay, so when the decision made, so this depending on decision.
Yeah, sure.
Depending on decision.
Sure.
So the decision after decision made, the action taken, this depending on what depending on action.
Sure.
So decision choose that link, you have the decision, right? Now what is this UI?
UI is the Q delay. Q delay.
Q delay for the agent.
Q delay for the package the agent just sent.
If we choose the package, so we remember this packet, how long the waiting is, the queue delay.
Sure. Waiting in the agent, the waiting buffer.
So this doesn't matter which action to take, but
Right.
independent of which action.
Right.
Okay. But ultimately, it will have each, because of collectively, each agent making decisions will affect the future.
Sure.
Delay,
Sure.
right?
Sure.
So that's each agent's decision. Okay.
We can consider this sum as the total time the packet spun on the agent, one agent, the Q delay and transmission delay, and we define the reward as a negative sum. Since if we do this, and the Q value will be a negative number, so when we try to maximize this negative number, it means we try to minimize the delay, total delay.
No. This is independent delay.
Independent delay.
But the action may not depend on delay. The action has no effect on the delay. For I and I.
Yeah, but the action will in fact the long-term delay of the packet.
Formulation is not correct, right? So this is for agent I, attempt to take action.
Yeah.
And from your definition of delay, right? There is historical, so this one will not impact. So this time the delay is constant. Already I know already the delay. How long? You need to choose action.
You already know this one.
Yeah, I already know that one. That one independent of action.
Sure.
Right.
Sure.
Mm-hmm.
The meaning of this Q function is, for example, if an agent if a packet is as a agent I, and we know the packet's destination, and this value will tells us how long it will take.
So what does that mean? QI, TI. S is the what?
S is the state, the destination of the first packet waiting in the agent's waiting buffer.
At T plus
1.
At T plus 1, right?
Right.
T plus 1, of course, is a different packet.
But here the state is the same. I didn't use the subscriber T plus 1. This one, this state is this state. the same thing.
Already by t plus 1, this path already moved to another loop.
Sure.
Right?
Sure.
So what is S now?
We can understand as fixed, as a fixed. It's just a destination.
So destination. So this packet destination, and then this packet can be anywhere.
Yeah.
Maybe not in node I, maybe not in that's node here now. Another node.
Yeah.
This is the all right. We probably cannot pass this. We don't know what S is. So the first view is
Okay.
S is the state at time t or time t plus 1.
S doesn't depend on T. Here, in this picture, each node can be considered as S.
Okay, so in this picture, the S, okay, don't move because S. So S is the so this probably S now.
Describe as
Yeah.
for example, if we have a packet here, and after we do the decision making to send the packet, we get a
S has nothing to do with the decision making. S is the state. Before you make a decision making, you have to know what's the state, right?
Yeah.
So describe to me what's the state.
S is the destination of the packet.
Okay, destination of the packet. So which packet? So S is the entire network, right?
Yeah.
So here has 100 packets here, there's another 50 packets here, there's 30 packets here, right?
Right.
So what's S?
At first, for the agent I, we will maintain a lookup table, Q table.
So there's agent 1, agent 2, agent something. State is the entire network, right? Are you talking about that? Or just one particular agent?
No, just one particular agent.
Okay, state is a particular agent.
Yeah.
One agent. So in that case, the T and the T plus 1 is different state. Do you agree?
I agree, but I agree, but the state is, the state is in this Q, in this function. It's not the state of the agent. This guy is just one destination, and this is a variable link, and we use the Q function to estimate the deliver delay.
Can someone help me?
So it's like we should think about the state as a combination of S and I and S and G, because the next state here you will use as a G. What is S? So you have transmission from let's say node I to node S.
For example, if there a packet at agent I, and we will choose a variable link, and then we will know which nodes the packet will arrive at next time. So I will assume it by J. And after the packet arrive at J's node 1, the reward will be
Does it take one time slot? At least one time slot?
one time slot.
But you said transmission delay, right?
Yeah.
Transmission delay is one time slot?
Yeah.
Exactly one time slot?
Exactly.
So the T plus 1.
Sure.
Transmission delay is always 1.
Sure.
Everything is the same.
Sure.
So there's no choice. Doesn't matter what happened. Right. So this is always 1. It's always 1, right? Yes.
Yeah.
So there's no choice.
It depends on the situation. In those papers, everyone says the transmission delay as 1, but if we apply this algorithm in real system, this it's okay to not be 1.
I give you maybe something that I think I'm afraid that we probably will not be able to do. Because so far we are maybe forget about what they did. Okay, something. Let's see if you do something that makes sense. Okay? This so far it doesn't make sense.
But this is not my paper. It's other paper, very famous
other
one.
Paper, right? Other paper so far doesn't make sense here. But this is we don't know what this is, and S and T plus 1, and
I will actually explain again.
So this is T, not T plus 1, right?
Yeah.
This is T.
Yeah.
This is everything doesn't make sense.
I mean, T is just a new estimation.
Oh, there's one operations on many papers. For example, if we once we do the decision making, and since in the communication networks the transmission delay is always doesn't have very high variance, so we can just it's okay to use this as a constant. And once the decision making is made, the agent I will send a signal to tell the J, say I will send a packet to you, and its destination is some node. So this guy can immediately send back some signal to tell the agent I this value. Actually, we don't have to wait for the packet arrive at the J's node to know this value and this value. So this is T, not T plus 1.
Okay, now let me just see if you can pass on some slides.
I want to try to explain this equation.
Right, no need. Okay, doesn't make sense. Go ahead. Maybe something that will work for you.
Do I have to explain the drawbacks of routing? And there will be some motivation about why do you want to use a policy-based reinforcement method.
Okay, go ahead. Policy-based. Yeah, what do you think? Not in the motivation.
Okay, and previously in Q-routing, each node will maintain a lookup table, two-dimensional, and the dimension is the available link by the sum of all the other nodes. For example, let's go back to this picture. For example, this node it has 2 available links, and there are 35 other nodes. So its Q table is 2 by 35. This is Q table, and expect this Q table in our method. We will maintain another table we call the policy table. It will store the preference for each state action pairs. Previously, the Q table, each element of the Q table is estimate of the delivery time of the state action pair, and we will maintain another table to store the preference, and we will use the preference to do the decision making according to the softmax rule.
So the general idea is the Q table, Martin table, too big, right? So it's too big to remember, right? That's the problem.
Not too bad. It's very small the size.
Martin table, Q table is small.
The same dimension. Q table and this table has the same dimension.
So what's wrong?
Nothing wrong. We will use another. We will add one more table. Q table will give us useful information to update.
Queue table is for each destination.
Yeah.
What can give me?
Each node, it will estimate the delivery time from the current node to the destination. We say the S. We say S here, and through one outgoing link. So it's state and it's action.
So I just choose the action with the smallest.
Yeah. This queue table.
Queue table is because the time, total time.
Yeah. For this packet. Yeah.
This is something that in essential that in essence that AlphaGo 0 is doing that it's accumulated on the color tree set to get that number. Right. So the action what's the chance the likelihood.
Yeah. But for the queue routing, if we only use the queue table to follow the greedy policy, then it's a deterministic policy. When the traffic load is very high, when traffic is load very high, and the agent doesn't distribute the incoming traffic, the incoming packets across the available links, so the congestion may happen. And in the reinforcement society, the optional greedy is always used to do the exploration and exploitation trade-off. But in our setting, this is not available anymore, since the traffic of the communication network is continuously changing. So the optional greedy never ends. In other reinforcement paper, the optional greedy will decrease. The optional, this value never end, meaning the exploration will never end.
Exploration never ends.
Yeah.
Okay. So what?
In other reinforcement paper, since the environment doesn't change, so we can use the optional greedy, and the greedy and the optional, the exploration level will decrease over time.
So what? As long as I deliver the package very nicely to the customer, to the consumer, I don't care you learning less or learning more. Right.
Right.
Because ultimately what you want to see is can you deliver enough value to the customer consumers in time. Right. So that's ultimately the goal, right? All right. Go on to see if you remove some of the issues.
I want to talk about this. And significantly, since the exploration never ends, it has a negative effect on congestion. This is the idea of the routing authors. They mentioned their drawbacks. We try to solve this problem.
Okay.
And one more important thing is.
I don't want something. I want something to the
Okay.
Kind of
so this is our policy.
Yes.
Through the according to the softmax rule. Then we want to use the.
So you need the parameters parameterized
by theta, the preference.
How many? What is the dimension?
The dimension of the theta has the same dimension of the queue table. The available link by the number of available links by the number.
Source destination path.
Yeah.
Source destination path.
Yeah.
Right.
Two-dimensional. One dimension is the number of available links, and the other dimension is the number of destinations. Two-dimensional table, and each element is a state action pair.
For each node starting origin, that's also the number of possible link out, right?
Yeah.
So you need for each pair of source destination, you also multiply by. So it's more than source destination, but each one the table the parameter how many links outside. So that's the each source destination. So it's for 50 million network. If there's completely one source to the destination combination, what's the number of variables? So for each of them have maybe 2 sources.
You mean 50 by 50 network?
It's a 50 million network. So the dots have 50. Each one has 2 possible links. What's the dimension of what's the size of the table size?
49. 98. If we have 50 nodes, 50 nodes minus 1 minus the current node. The current node don't have to maintain some estimate to itself. So it's 49 times 2. Since each node have 2 available links.
So that's for each and one.
Yeah.
That. But every node.
Sure.
So the 50
But each node only have to maintain the true table of itself. It don't have to maintain other people's true table. So the parameters one agent need to store is 98.
Okay. So that's the setting of the policy taking decision pay high based on that. Like based on
Yeah.
Okay.
Yeah. We will also maintain the Q table.
You also maintain Q table.
Yeah.
Q table is the Q function policy. So this is we are taking the active framework.
Yeah.
Right. Active framework, and we do the traditional landing. Like active landing, right?
Yeah. We propose 2 algorithms. Yeah.
So nothing neural network here.
Nothing neural network. Nobody can use network in this problem setting. Many people have tried, but no one succeed.
Okay. So go on to show me the results.
Numerical result.
Yeah. What's network for example?
Here is the we have shown this topology, this network in regular 6 by 6.
The same picture?
Yeah, the same.
Same picture before? What is the each node has an external router?
No.
A source, right? Each node is a source. Also.
Yeah.
Each node is a source and also can be destination, right?
Yeah, right.
So the traffic coming from the source, how much traffic?
Yeah.
Do you have some specification for that?
We use the Poisson process to simulate the arrival process. And for example, in this time slot, once one packet is injected into the network, we will uniformly choose one source or one source. And
so there's one Poisson stream. Each packet is uniformly distributed to this node.
Yeah.
That's fine. And do you know the load of this network?
Here is a load. Network load.
What does that mean?
12
meaning what?
12 meaning the parameter of the Poisson process. 12 meaning in one time slot, average there will be 12 packets injected into the.
Fine, that's good. And so some explode earlier.
Yeah. This is the shortest path.
Okay.
Shortest path.
So the cannot handle more than 6. Right?
6. Yeah.
6 is the maximum load.
Yeah.
And then what's the dash line?
This is Q routing. I talk about
it. Routing at 10 is already.
Yeah.
It's not to the limit. Okay. The last one is.
No, the 2 algorithms, but their curve it's very similar.
Okay, 12.
Yeah.
What are they?
Our algorithms. We propose 2 algorithms.
The 2 hybrid. We just talk about that.
Yeah.
And there's also another yet to be
Yeah.
described, multi-agent.
Yeah, multi-agent one.
Just don't move away.
We
Do you
have
know, do you know the 12 theoretical limit?
uh,
Is no algorithm can do better than 12? Or you don't know?
I don't know.
You don't know.
I don't know.
Have you tried max back pressure policy?
No.
Do you know what back pressure policy is?
No.
Study it. Okay? Back pressure policy. So try that simulate back pressure policy. Can they push up further?
Okay.
Okay.
In most reinforcement papers, we compare with other reinforcement method and plus the short.
Yeah, I understand. But something.
I understand. I will do that. I will do
You
that.
want to do better, right? You want to do something the best thing. This is the best thing. Right? So that's the. You have two things. I mean, what's the y-axis?
It's an average packet delivery time.
So what's how much time? What's the time is right? Okay.
Yeah, average.
Average time is right.
Yeah.
So that's the measure. That's the dot to dot time. Dot to dot.
Yeah.
So very good. Okay, so I want you to. I think at this point I don't maybe. Maybe let you talk. Yeah. Okay. So this is something that I want to see that back pressure point. Okay. And I can quickly tell you a paper. This paper this year. I'm one of the authors there. Okay. You can try the algorithm there. That we submit paper. Okay. Cover your model very well. Okay. Completely cover your model. This experiment should be done in our paper. See, you can compare. We have several family parts. Much simpler policy.
There's another network, larger size, 160 node. Telephone network. This one is shortest path. This one is routing and.
Very good. Okay, this is something that if we can, if they can beat our policy, that will be really impressive. Okay. Now, our policy is very market. Depending what information you want, we need to know the queue size of net downside.
Yeah, we don't know.
You don't know.
I don't know.
So that's maybe the most something. So I need a sort of cheaper bit. I need to know some immediate neighbors. Neighbor tell me what's your queue size.
Yeah.
But here you don't know the neighbor's queue size. But you do know the how long the neighbor information get updated to you.
Yeah.
Through what?
Through the reward.
Through the reward.
Yeah.
But the reward is that's why I'm chasing you. What does the reward?
Oh.
The reward you cannot get something.
Yeah, I have mentioned the feedback signal.
Yeah.
Once agent send one node to its neighbor node,
Yes.
The decision make once the decision making is made, the neighbor node will send back its Q value, one Q value. That I think is very important.
So if you send one Q value, the neighbor can send me updated my buffer information. Right? That's certainly easy.
Yeah.
Do you agree? The neighbor can send me that I currently have 5 guys with.
Yeah.
It's easier than update your Q value. Right? I mean at least as easy as that. Right? So information wise, I mean our average is not anymore.
Yeah.
I just need a neighbor tell me. Maybe there's slight delay. Okay, here the Q value is no delay. You said immediately feedback, right? That's your some instruction. Feedback. So essentially, you need to know the neighbors information. All right.
If we know the neighbor's information,
But you do know. You assume you know.
yeah. I don't. Yeah, sure. I know.
Do you agree, right? You said, oh, I don't need to know the neighbor's information, but you what neighbor's information give the feedback.
Yeah.
Q value.
Yeah.
Right?
Yeah.
I said sending that information instead of sending 1 bit, 2 bits information, but Q size, just something that's even as easy as that.
Yeah.
All right. So I don't think we should get into detail about the critical. One single agent is very clear. Okay. No, this is global. The active critical in the sense of this is each agent. In our case, the active predict is often centralized. Right? Centralized. When is he made?
We modify the actor predict. Actor predict use reward plus the value function minus the value function. We use Q function. I refer this part to Professor Benjamin Monroe's notes.
This is the second one. Is that an advanced function minus something?
Yeah. You mean this part?
Yes.
Not advantage function. Advantage function is the reward plus a Q value minus a value function. Here we compare with the best Q value. We compare with the best choices to know whether the decision.
Very similar.
Yeah, very similar.
Right?
Very similar.
That the point that term doesn't depend on the action. Right?
Yeah.
Okay, so this is the hybrid method that
using the Q learning and active predicting, very similar to active predicting method.
Yeah. What about hybrid one? What's the multi-agent?
Multi-agent, multi-agent is a little bit different. We introduce the eligibility trace, and we update. We use some global signal to update the parameter of each agent. Here we introduce, we talk about the joint state and the joint action of the network, and we try to decompose them in this form.
So multiple agent meaning what? Not each agent has to make each node independent state, but global nodes as addition. What do you mean multi-agent?
At a time slot, each router do the decision making independently, but we will try to use a global feedback.
So not just neighboring information.
No need.
Global information feeding different.
Yeah.
Is that truly global or is it some subset of global information?
What
Truly, the meaning entire network state you have feeding into all the single state, each node, or just part of the network, or entire network feeding into each node.
The whole network.
So why is this called multi-agent?
Not multi-agent, not multi-agent one.
This is not multi-agent.
Yeah, this is not multi-agent. We use single agent algorithm. We apply single agent algorithm to the communication network system. Yeah, but we can also say the routers multi-agent.
So really, you're talking about the two algorithms here. Remember, you have two hybrids, right?
Yeah.
The second one, I saw the title multi-agent.
Yeah.
But it's misleading. It's not multi-agent. Yeah. It's the information, more global information for each agent.
Yeah. There also other papers do the same thing. They also use the single agent algorithm and they call the multi-agent. I think it's a very interesting paper by Peter and Peter Ballard. We had and Terence Tau's brother. This paper.
Give me talk.
Yeah. His advisor proposed a very famous algorithm to estimate the policy gradient on infinite arrays.
So I think I got enough, and I think I want you to see the example that I tested, okay, on this new algorithm, okay, a few algorithms So I'm going to tell you about, maybe sending yeah.
Okay.
These are the very information exchange of the policy. So potentially, particularly, I want to see if the line, the line can move further to the right, right? So if the line can be moved forward right, then of course it's error in the implementation, right? Not reaching the full network. I think you guys can continue. Okay, I think it's better for me to stay out of it so that we can properly communicate other people can make sure that other people understand. Okay. Maybe after 10:30 something, you could come over.
Is that coincidence or is that just the algorithm that we have two simulations? One is you said it's a 6x6 irregular topology, right? That I guess that's less than 36 nodes.
Yeah.
That's exactly 36 nodes.
Yeah.
Okay, well, yeah, I see that. And the second simulation you showed is 116 nodes.
Yeah.
And both are threshold is for their queue routing is at 10. For your 2 algorithm is at 12. Right? The shortest path one is like
Sure.
right. Is that scalable like the algorithm, or that's just a coincidence here? What I'm saying is that if you have a very big network, a very small one, do you like also hit it like 10 and 12? You see what I mean?
We just do experiment on this two connection network.
I understand, but oh, okay, all right. So you said that you only did.
But one important point is the routing is unrealistic. If you use grid policy, once the traffic load is increased from low level to high level, it works. If it decreases high level to low level, it never works. It won't work.
Okay.
For routing, like this is real system.
I see. Because I see there that also the gap is 2, right? You always have a gap of 2. Seems to me. There's one is 12, one is 10. Right, for your two simulation.
You mean it's
yeah, the kind of the tolerance arrival rates you can have.
Yeah.
What discount factor did you use? What discount factor did you use? In your algorithm, what value of the discount factor? Discount factor.
For the Q function, the discount factor may be 0.9. I don't remember. 0.9, 0.8. I use actually two discount factors. One for the AI trace and one for the Q function. We need to combine it together. Here the D is the database.
Okay, so why do you have? Oh, you mean lambda? Okay.
Did you have to tune those things, or did you have to tune the discount factor, or you just did as the digit?
In our experiment, we will choose the discount factor to help us obtain the max traffic load, and then we fix don't you never and test it in the dynamic changing networks.
Okay. Any other questions?
Along this one, this max, what's the motivation for
in communication networks, traffic situation of each node will change quickly. And if we can use the queue function and get the reason information, and we can also compare with the max. We also compare with the best choice. We will know whether the choice we just made is good or not.
I mean, yeah, basically this.
Yeah, and in multi-agent system, we use the max node, and we get a way to parameterize, to decompose the joint action. Although it's input.
So what is S here?
You mean
Yeah, what capital
capital
S? Yeah, what's capital S?
capital one?
Okay, what's the state then? Because I mean, did you guys put this S on the slide? So maybe, yeah, okay, thank you.